Welcome back to Codex. Our speaker today is Travis Russell, who is a postdoctoral research associate at Dartmouth College. Dr. Russell's research interests include quantum information theory, operator algebras, and machine learning. Today, he will tell us about quantum correlations via operator systems. Take it away, Travis.
Okay, thank you. Feel free to ask questions if you feel comfortable doing so with the mic. I'm not super great at keeping track of the chat, but I can get to chat questions at the end if I don't see them. So this talk is about, way to motivate it, I suppose, is to say it's strategies to playing certain kinds of multiplayer games. And these are sort of essentially quantum strategies for playing these games. I don't know if this kind of thing comes up in this seminar. I might be a bit of a fish out of water. So at the end of the talk, I'll try to make kind of a vague connection to between this work and seek POVMs and mutually unbiased spaces, which I think do come up in this seminar sometimes. So hopefully I make it that far and we can at least make that connection in case these other things maybe aren't as interesting or relevant to some of the audience. Okay, so that being said, let me get going. And this is joint work with Roy Areza, who's a postdoc at Urbana-Champaign, and Mark Tomford, who is at University of Colorado Springs. So I want to start by introducing this idea of what I call a non-signaling game. Sometimes in the literature, it's called a non-local game, or sometimes people will just say it's a quantum game. But the definition of it, there's nothing really quantum about it. You have, it's a multiplayer game. For this talk, we'll just have 2 players, but most things will generalize to more than 2 players. So my 2 players will be Alice and Bob here. And they're going to be asked questions and they have to provide answers to those questions. So we have a finite set of questions Q. We have a finite set of answers A. And then there's some rules to the game, which are tuples, 2 entries from Q and 2 entries from A. And the way the game works is as follows. The referee is going to pick 2 questions, X and Y, from the set of questions. He sends question X to Alice, question Y to Bob, and then Alice and Bob respond. Alice responds with answer A, Bob responds with answer B, and they will win that round if the tuple X, Y, A, B is in this set of rules. Otherwise, they lose the game. Okay, so that's basically how it works. Some things I should mention. So Alice and Bob know the rules in advance. They know the set of questions. They know the set of answers. We can also assume that they know the, say, probability distribution through which the referee will pick the questions X and Y. So we know the likelihood of a question pair X comma Y being asked. What they don't know is what question was asked of their colleague. So Alice does not know that Bob received question Y, and Bob does not know that Alice received question X. And so they have to come up with their answers A and B without knowledge of what questions were asked. And so you can imagine, I'll do an example in a moment, but you can imagine this might make it impossible to guarantee that you will win the game. And so you may want to consider like probabilistic strategies for playing this game. And so we'll describe a lot of strategies in terms of probability distributions. So I'm going to define that now. So the kinds of probability distributions that we'll be using are called correlations in the literature. It's kind of a misnomer and different authors use different words, but most people use the term correlation, so I'll stick with that. So correlation is a tuple of numbers, which we index as P, A, B, X, Y. So A and B are coming from our answer set. X and Y are coming from our question set. These are positive real numbers. They sum to 1 if I sum over the A and B in the answer set. So basically, it's just a joint probability distribution. But we're going to be interested in the kinds of correlations that would arise in this scenario where Alice and Bob cannot signal each other, where they're not allowed to communicate. They don't know what questions are asked of each other. So we codify that with these non-signaling conditions. So a correlation is called non-signaling if it has well-defined marginal densities. So we can talk about the probability that Alice responds with answer A, given that she was asked question X. And you define that mathematically by just summing over all of Bob's possible answers. And implicitly, the sum depends on the question W that Bob was asked. So to say this is well defined means that it doesn't matter what question W is asked. No matter what W Bob gets asked, the sum yields the same value. So that's what I mean to have a well-defined marginal. We do the same thing for Bob, summing over Alice's answers. So as long as, after many rounds of the game, if the probability distribution satisfies this condition, we can say that they're not communicating or they're not taking advantage of any kind of communication. Okay. So these are called correlations. This will be sort of the star of the show today. Here we go. So let me give you an example of one of these non-local games, and we'll talk about different kinds of correlations and strategies in terms of this game. So the game I'm going to consider is the two coloring game. You can play this with any graph that you want. For our purposes, we'll just consider a 5-cycle. So the goal of the game is to convince the referee that that Alice and Bob have produced a two coloring of the graph. Now, if you look at the graph, it's not possible to two color this, right? So a coloring is an assignment of colors to the vertices. Let's say our colors are red and blue. I want to assign colors to the vertices such that any two distinct edges that are connected by, or distinct vertices connected by an edge have different colors. So it's easy to see that's not possible here. So what strategies could Alice and Bob use to fool the referee? So some more details about this game. The referee is going to ask questions. We're going to assume that he selects the questions uniformly from this set. So he's either going to give Alice and Bob the same question pair, or he's going to give Alice question 1 and Bob question 2, or Alice question 2 and Bob question 3. And if Alice and Bob receive the same vertex, if he asks 2, 2, for example, they're going to win the game if they return the same color. If they receive adjacent vertices, they're going to win if they return different colors. And we want to find a good strategy for playing this game, given that we can't actually color the graph. So we might come up with some kind of probabilistic strategy for this, or we might do something else. So let's start with kind of the simplest kind of strategy, which is what I'll call a deterministic strategy. So we're going to call a correlation deterministic if the marginals are all either equal to 0 or 1. And this is equivalent to saying that there's a deterministic way of selecting answers given the question that you're asked. So we can imagine Bob has a function, or excuse me, Alice has a function f and Bob has a function g. And if Alice receives question x, she's going to respond with answer f of x. If Bob receives question y, he'll respond with answer g of y. So that kind of strategy is going to produce one of these deterministic correlations. There's a 100% chance that Alice responds with answer f of x, given she was asked question x. Okay, so in a two coloring game, what's a deterministic strategy look like? So here's an example of one that you can use. You can sort of write down a coloring of your graph that's almost correct. And there's ways to do this where you can win 90% of the time, given the things I told you on the previous slide. So here's an example. I'm going to choose this coloring. Alice and Bob will each take a copy of this coloring. The referee doesn't know about it. He's still going to select, questions randomly. The only way you can lose is if Alice receives question 3 and Bob receives Alice receives vertex 3 and Bob receives vertex 4. Otherwise, they're always going to win. So basically, the functions here are, f of 2 is blue, f of 4 is red. So you just use this graph to produce your answers. There's only one way to lose when they receive question 3, 4, and that has a 10% chance of happening according to this distribution we assume. So 90% chance of winning with this deterministic strategy. Okay, so let's try to think of a more creative way to play the game. So another type of correlation that we consider in the literature is called a local correlation. Local correlations are just convex combinations of deterministic correlations. So I have some deterministic correlations, P1 through Pk, and then I'm going to sort of randomly select one. And one way you could produce this is you could imagine that Alice and Bob have access to like a random number generator. So there's some machine that's going to produce a number between 1 and k, some number I, with probability ti. And whenever you play a round of the game, in addition to receiving the questions, they'll also receive this random number. So they both get the number I. And so then they go through and they use their ith deterministic strategy to play the game. That's one way you can think of these things. So deterministic strategies plus some sort of shared randomness. So in this 2-coloring game, it turns out that this doesn't improve your chances any. You still win 90% of the time with any local strategy. And there's a reason for this. I'll talk more about this later, but you can think of the set of correlations as a convex set in Euclidean space. And finding an optimal strategy for a game is like maximizing over that convex set. And so the local correlations actually form a polytope. And so if you can sort of maximize with some point on the polytope, some extremal point, well, you could also optimize with like a vertex of that polytope, and the vertices are going to be deterministic. But, okay, so local correlations, same, it gives you a convex set now, but it's the same likelihood of winning. So now let's do something more interesting. I'm going to do something kind of like the random number generator, but it's going to be fancier. It's going to be a quantum random number generator. So I need to go through the obligatory introduction to quantum mechanics in 4 bullet points. My apologies to the experts in the room. But for us, we're going to think of physical systems as corresponding to Hilbert spaces. So these are just vector spaces with an inner product. They could be finite dimensional, they could be infinite dimensional, and I'll try to clarify which it is. The state of the system is a unit vector in that Hilbert space. And given a physical system, I can perform measurements, a physical system in a state, I can perform measurements on that state. And measurements for us are going to correspond to projection valued measures. We'll just have finite ones here. So for us, a projection valued measure is a set of M operators, projection operators. So they're Hermitian, they're idempotent. When you square them, you get back the original projection. And when you sum them up, you get the identity operator. So they behave kind of like a probability distribution. And so with this setup, you're going to observe outcome A. So A is a number between 1 and M here with this probability. So this is an inner product. I do P times phi and then inner product with phi. You can check that's the same as calculating the norm square of the vector PA phi. The PAs are basically just projecting your vector onto a subspace. And since you started with a unit vector, this always gives you a probability distribution. So a very fancy random number generator. At the end of the day, we produce a random number between 1 and M. So let's see if this changes the outcomes of the game at all. So now, given that, that background, I'm going to define a quantum correlation. So quantum correlation, correlation P is called quantum correlation if we have a pair of Hilbert spaces, one for Alice, one for Bob, and these will be finite dimensional here. A unit vector in the tensor product of those Hilbert spaces. And then a set of measurements, 2 sets of measurements, one set for Alice. So the E's act on Alice's Hilbert space. So for every question X, you get a new measurement corresponding to X. And then the Fs are measurements on Bob's Hilbert space. For every question Y, he has a new measurement, FYB. And the probability that Alice and Bob respond with A and B, given that they were asked questions X and Y, comes from this inner product here. And roughly what this would look like physically is Alice and Bob have sort of laboratories where they're going to be answering their questions. When the referee sends question X to Alice and Y to Bob, he's also going to prepare this unit vector phi in the tensor product of the Hilbert spaces. So you can think of this as like 2 qubits or something. He sends 1 qubit to Alice, another qubit to Bob. They can each perform measurements on their separate qubits and use that to produce answers. Okay, so that's the setup. Let's go back to the 2 coloring game. So this is a result of Cleve, Hoyer, Toner, and Watrous. In this 2 coloring game with the 5 cycle, if you look at all the different quantum correlations and quantum strategies for playing the game, you can actually win the game with a probability of 97.6%. So you get a significant improvement in your ability to win the game by considering these quantum correlations. So that tells you that it's not just a random number generator. It's not just a fancy random number generator. It's doing something that's essentially different. And that's because of entanglement. So if I have a unit vector in a tensor product of Hilbert spaces, I can always write it as a convex combination of these elementary tensors. So the psi I is a unit vector in Alice's Hilbert space, rho I is a unit vector in Bob's Hilbert space. Any vector can be written like this, but this expression is not unique. So there's various ways you can express a state phi, and phi is called separable if you can write it as just a single elementary tensor. Phi A is a unit vector in Alice's, phi B is a unit vector in Bob's. So that's a separable state. Otherwise, phi is called entangled. And I'm going to attribute this to John Bell. This isn't really something John Bell would have said in this language, but it kind of follows from his ideas. So it turns out that if phi is separable, the quantum correlation you get from doing these things I told you on the previous slide, it's just a local correlation. It really is just a random number generator. So that tells you something. If you play one of these games and you're beating the best local strategy with some kind of quantum strategy, your state has to be entangled. So this can be seen as kind of like a test for entanglement. And this is roughly how we were able to kind of, well, not we, but humanity was able to kind of prove that entanglement is a real thing in a laboratory. You can actually set up these kinds of quantum games with lasers and things and actually look at the probabilities that you get and see that you can outperform these local strategies. Okay, so that's a quantum correlation. I have one last type of correlation to introduce, and then I'll talk about all these different correlations and how they relate to each other. So the last type I want to mention is sort of an infinite dimensional generalization of quantum correlations. So a correlation is called quantum commuting. If there exists a Hilbert space H, a unit vector in that Hilbert space, and then measurements, again, we have E's for Alice and F's for Bob, but they're not acting on separate Hilbert spaces. So H is not necessarily HA tensor HB, it's just a single Hilbert space. All I require is that Alice's measurements commute with Bob's. So you can think of these as, they're operators on a Hilbert space. You can think of them as matrices. Those matrices commute is the requirement. At least all of Alice's matrices commute with all of Bob's. And then we can produce a correlation with the same inner product formula. So with the 2 coloring game, it turns out that this kind of strategy, this kind of correlation will produce the exact same win probability. And so then you might wonder, well, is this really doing anything different? If you hand me oh, I should mention something actually. The Hilbert space H here is potentially infinite dimensional. If it happens to be finite dimensional, you get a quantum correlation. There's a way of rewriting this expression in terms of a tensor product of Hilbert spaces. So, so you really need infinite dimensional to potentially get something new. But even if you look at infinite dimensional Hilbert spaces, this is no better. You still win with the same probability. And so you might wonder, is every quantum commuting correlation really just a quantum correlation? Is there some finite dimensional way to produce the same numbers? Or is there a sequence of finite dimensional quantum correlations that approximate that same value that would also give you the same optimal win strategy? So these questions go back to Tsirelson. So I'm going to introduce some notation here. Let's say we have n questions in our game, m answers. We'll let C sub star in m denote the set of all correlations of a particular type. So star here is a placeholder. So all these correlations I've described fit into a nice hierarchy. The local correlations are the smallest, followed by the quantum, then the quantum commuting, and then the non-signaling. And I can think of all of these as points in Euclidean space. So these are tuples with two entries from Q and 2 entries from A. So I can think of them as just points in Euclidean space. They all turn out to be convex sets. And the local, the quantum commuting, the non-signaling, those all turn out to be closed sets. The quantum, it's not clear if it's closed based on the way it's defined. But we have this hierarchy. And so there's a lot of interest in, can we separate these sets, and what values of n and m allow us to separate these sets? So John Bell's early work on the EPR paradox back in the 60s separates the local and quantum correlations. It basically says that entanglement is a real thing. And that works as long as n and m are at least two questions, 2 answers. Tsirelson started asking questions about these sets in the 80s. I guess I should say something about that. I believe he originally conjectured that the quantum and the quantum commuting were the same. And when people asked him about it, he realized it wasn't so clear, and he posed this as an open question. Is the quantum the same as quantum commuting? Or is the closure of the quantum the same as the quantum commuting? And it turned out this was a very deep question. So 2011, two independent papers showed that a positive solution to the Kahn embedding problem from operator algebras, which was first asked in 1970 or so by Alain Kahn, that would imply that the closure of the quantum is equal to the quantum commuting for all possible question and answer sets. And actually the converse was quickly proven as well. So a couple years later, Ozawa showed that if you have this equality for all question and answer sets, then the Kahn embedding problem is true. So this is a problem that operator algebraists had been very interested in for a long time and had lots of equivalent formulations, but hadn't really had progress on it. And so this was seen as maybe we can compute something and answer this question finally. Okay, so 2017, William Slofstra proved that the quantum is not the same as the quantum commuting. What he actually showed is that the quantum correlations are non-closed for certain values of n and m. So in his paper, he had a question set with 235 questions and 8 answers. In the literature, it's been simplified a bit. You can actually go all the way down to 5 questions and 2 answers. And there's some other scenarios as well where you get this non-closure. It's still an open question for 3 questions and 2 answers. So in these small settings, it starts to get tricky. But we know that in some cases, the quantum correlations are non-closed. So that's not the quantum commuting. But then you can still ask, what about the closure? That's the hard question. It's equivalent to this open problem. And so that was finally answered in 2020 by these authors in a preprint called MIP star equal RE. They showed that, so the proof is computer science going through complexity theory. And they showed that there has to exist some question and answer sets for which these things are non-equal. And the proof is kind of non-constructive, but they still have an estimate of this happening somewhere around 10 to the 20th questions and answers. Okay, so that settles the Kahn embedding problem. It says there's a negative solution to the Kahn embedding problem. But because the paper is kind of non-constructive and uses a lot of ideas in computer science, there's still a lot of interest in people in operator algebras where I come from, in trying to approach this maybe from a different direction, or maybe trying to find some kind of more an easier solution, I guess, if such a thing exists. And so that's something that I'll be kind of talking about. Not that I have a solution, but I have a different approach that might hopefully be viable someday. Okay, so I'm going to switch gears a bit and start talking about more algebraic things. Sort of how do you get these correlations from abstract structures, algebraic structures? And there's two kinds of structures that I'll be talking about: C-star algebras and operator systems. So let's fix a Hilbert space H. A C-star algebra is a self-adjoint closed unital subalgebra of the bounded operators on that Hilbert space. An operator system is a self-adjoint unital subspace of B of H. So the operator system may not be closed under multiplication. C-star algebras that we'll be considering are generally infinite dimensional. The operator systems that we'll be considering are mostly finite dimensional. So that's what a C-star algebra is. That's what an operator system is. And in operator algebras, we usually, we don't always work with this definition. This is sort of the concrete definition. There's also abstract ways to define C-star algebras and operator systems, which are sort of equivalent. So for a C-star algebra, it's a star algebra with a norm whose norm satisfies this C-star condition. And once you have such a thing, you can prove it's isomorphic to one of these concrete subalgebras of B of H. You can construct the Hilbert space and so on. We also have abstract operator systems. These are star vector spaces, so a vector space with some kind of involution that acts like the adjoint, together with a sequence of positive cones at different matrix levels. So I can take my vector space and I could consider n by n matrices with entries in that vector space that has a natural involution. And then I assume I'm given, as part of the data of this abstract operator system, a cone of positive elements inside each of these cones. And I also have a unit. And of course, there's some extra conditions I need to relate the cones and the unit, but I won't describe those here. And given an abstract thing, I can produce a concrete thing. So given an abstract C-star algebra, I can produce a concrete C-star algebra isomorphic to it. I can do the same with the operator systems. Okay. A state on a C-star algebra is just going to be a linear functional, a linear map from the algebra to the complex numbers, which sends the identity to 1. And when you feed it a positive number, a positive element of the C-star algebra, you get a positive real number. So positive elements in the C-star algebra are elements that factor is, say, B star B for some B in the algebra. And you can make the same definition for operator systems. If I have an operator system, that's a vector space with these defined positive cones, and so I can ask for, and a unit. And so I can ask that the linear map send the unit to 1 and send positive elements to positive numbers. Okay, so you can redefine quantum correlations purely in terms of C-star algebras. And this is kind of folklore. I think maybe the first statement that I know of is in a paper by Junge and his collaborators that I mentioned earlier. But it turns out that you can describe everything, all these different types of correlations just in terms of C-star algebras. So if I have a tuple P, which is a correlation, it's quantum commuting if and only if there exists a C-star algebra, some projection valued measures which commute with each other, and a state, a linear functional on my algebra for which I get PABXY by just applying phi to these products. And you define all this stuff without reference to any Hilbert space. Projections are just self-adjoint things. When you square them, you get back to yourself, and so on. So it's a purely algebraic definition. So I can get quantum commuting correlations from this algebraic definition. I can also get quantum correlations if I add the restriction that my C-star algebra be finite dimensional. And I can get local correlations if I add the restriction that the C-star algebra is commutative. So we can phrase all of this in terms of C-star algebras. Now I would argue that this is maybe a little bit inefficient. And the reason is, to get a quantum commuting correlation, let's say, I need an entire C-star algebra, which is usually going to be infinite dimensional. But then to get the correlation, I just apply phi to a finite number of elements. It's just these products of EXAs and FYBs. But there's another path that maybe you could take, which is to take those products and form an operator system from it. Okay, so if I have a correlation that's quantum commuting, I can get it by applying phi to these elements. But I could also consider the span of these products, the linear span. That's an operator system. It's self-adjoint, it's unital. And so anytime I have a quantum commuting correlation, I can write down this operator system, and I get the correlation from applying a state to that. Okay, well, we have an abstract notion of an operator system. It's just a vector space with this order structure. Is there a way that I could take one of those abstract operator systems and pull correlations out of that? It might be nice because these operator systems are finite dimensional. You still have the infinite data of all the positive cones, but there may even be a way around that, because the state, the positive linear functional, really only cares about the positive elements of V. It doesn't really care so much about what happens in these higher matrix levels. So it might be possible to take an essentially finite dimensional thing, something we could actually write down, and then pull correlations out of that. And that's kind of the philosophy of why I got interested in these things. My colleagues and I should say. So what I'm going to do is try to abstractly characterize operator systems of this form. So an operator system, if you're handed an abstract operator system, it's always isomorphic to a concrete operator system, an actual one. But you don't have a multiplication, so you have no way of identifying projections or things that are products of projections like this. So the question is abstractly characterizing these particular kinds of things. And so to do that, I need to understand what a projection is in an operator system. And it turns out there's a way to do that. So the first thing you actually consider is compressions by projections. So let's suppose I have a concrete operator system. So it's sitting inside an honest-to-God Hilbert space, or acting on an honest-to-God Hilbert space. And let's say there's an element P in that operator system, which is already a projection. It turns out that the compression of an element by P, a Hermitian element by P, is positive if and only if for every epsilon greater than 0, there exists a T greater than 0 such that this linear combination is positive in your operator system. So what's nice about this is this is the abstract data. I can write, as long as P is an element of my operator system, I can actually write down these kinds of expressions. And I can look at the positive cone and see if you're in there. So somehow from just the abstract data, we can derive some sort of essentially multiplicative behavior. We know that compressing things gives me positive elements. Okay, so I'm going to take this idea and use it to figure out which elements of an abstract projection, an abstract operator system are projections or can be realized as projections in a Hilbert space. So again, let's assume we've got an honest operator system acting on a Hilbert space and an honest projection in that system. Let's let Q denote the identity minus P. That's also a projection. Now I can take an element X in V and I can rewrite it as a 2x2 matrix. So what I'm doing is taking the Hilbert space and decomposing it as the range of P direct sum the range of Q. Okay, so now I have X as a 2x2 matrix. And now what I'm going to do is take X, I'm going to inflate it to make a 4x4 matrix with X's in the entries. Okay, so I'm thinking of each of the X's as, this is a 2x2 matrix of X's, but I'm thinking of each of those X's as 4x4s. So now I've got this big 4x4 matrix. I compress it by P direct sum Q. That gives me this matrix here. And if I blur my eyes and look at this 4x4 matrix on the right, I see that it's the same as the original matrix, just sort of with a direct sum of a 0 matrix in there. So that tells me that X is positive, the original operator was positive, if and only if this 4x4 matrix has positive compression by P direct sum Q. And that's nice because I can detect when this has positive compression by P direct sum Q using only the data of the abstract operator system. So I can forget about the Hilbert space and I can just check this condition. And it turns out that that actually characterizes things that can be realized as projections in an operator system. Okay, so you have to write down, take those previous two slides and combine them into a definition. So we'll call something, an element P, an abstract projection, if whenever a Hermitian element satisfies this condition, for every epsilon, there exists a T such that this thing is positive. We ask that that's equivalent to just saying that X was positive in the first place. If P satisfies this condition at every matrix level, so X is sitting in all these different, at all these different matrix levels here, then we call that an abstract projection. And it turns out if you have such a thing, you can build a representation of your operator system that sends P to an honest projection. Okay, so given let's say we have a positive contraction P and an abstract operator system, then P is an abstract projection if and only if there exists a unital complete order embedding, essentially an isomorphism, mapping V to B of H and sending P to a projection. Okay, so this kind of complicated looking condition tells me which elements of V are actually projections. There's a catch here. So the theorem only tells you that you can do this for a single projection at a time. Maybe you have a whole bunch of abstract projections. This pi might send one projection to an honest projection, and it might send the other abstract projections to just some positive contraction, something that's not a projection. There's a way around that using something called a C-star envelope. So a C-star envelope is a special C-star algebra that you can always embed your operator system into. I won't say much about it other than it's sort of like the smallest C-star algebra that contains a copy of V. And it turns out that every abstract projection is a projection in this C-star envelope. So if I have, in particular, if I have a finite set of projections, which is the situation I'll be interested in a moment, they're all going to be honest projections in the C-star envelope. Okay, so now I can define a way to get these quantum correlations out of operator systems. So I'm going to define a quantum commuting operator system to be a finite dimensional operator system with a unit E spanned by some positive contractions Q, A, B, X, Y. So they're indexed the same way we index a correlation. Sorry, this M, bracket M is like the number set of numbers 1 through M, bracket N is the numbers 1 through N. And then I'm going to ask for these vectors in this vector space to basically satisfy the same properties as a correlation. So if I fix X and Y and I sum over A and B, that gives me the unit. And I also have well-defined marginal vectors. So it's the same sort of marginal density formula we saw earlier, but I'm summing vectors in my vector space rather than the numbers. So I ask that these marginal operators be well-defined. So I have non-signaling conditions for the basis of my vector space. And finally, I ask that each of the Q's be an abstract projection. in this operator system that satisfies these complicated conditions I mentioned earlier. So it turns out if I have one of these things, I can generate correlations by applying states to it. So with my colleague Roy Areza, we proved that a correlation is quantum commuting if and only if there exists one of these quantum commuting operator systems and a state, a positive unital functional on the system for which PABXY is just the state applied to the generator's QABXY. And some things that went into the proof, just the fact that we enforce these non-signaling conditions on the QABXY, that ensures that PABXY is a non-signaling correlation. That's easy to check. Because they're all abstract projections, they give you honest projections in this C-star envelope. And then this is kind of the tricky part. It turns out that once you know these are actually projections in some C-star algebra, they naturally decompose as products of projections, which is what I needed in the definition of a quantum commuting correlation. Okay, so I have a way of getting quantum commuting correlations out of these abstract vector spaces. But there's these other kinds of correlations as well. Can I get them? And it turns out there's a way to do that too. So we have to add a condition that the operator system is k minimal. So k is a positive integer here. So an operator system is k minimal if I can think of it as a subsystem of a direct sum of k by k matrices. And so I'm thinking of it as just a block this is just block diagonal k by k matrices on the blocks. This could be infinite set, this I here, or it may be finite, it doesn't matter. So it turns out you can detect this k minimal condition by just looking at the ordering that you're given for an operator system. So V is k minimal if and only if I want to know the positive elements at levels higher than k, I can get them by just sort of conjugating k by k matrices with some scalar matrices. So you get all the higher levels by just sort of blowing up the k by k level. So basically, these are essentially finite dimensional things. You have a vector space, and if you know what the positive cone looks like at the kth level, you know everything that you need to know about the operator system when it's k minimal. And we'll say an operator system is matricial if it's k minimal for some k, some finite positive integer k. So it turns out if I take a quantum commuting operator system and I add the condition that it's matricial, that's going to give me quantum correlations. So this is joint work with Roy and Mark Tomford. Correlation is quantum if and only if there exists a matricial quantum commuting correlation with these generators and a unital positive linear functional for which PABXY is apply the state to the generators. So the first theorem I described tells you that whenever you do this, you get a quantum commuting correlation. And then the hard part of this was showing that this C-star envelope, where all the Q's are projections, is actually can be realized as a subalgebra of a direct sum of k by k matrices. So it's kind of almost finite dimensional. And then what that does is it breaks your correlation into this infinite convex combination of quantum correlations. And then you use Carr-Theodori's theorem about convex combinations of elements in Euclidean space to show that you can actually get by with just finitely many of these, and now you get a quantum correlation. So the proof was a little bit tricky. And I'll add, I don't think I put this in my slides, if the space is actually one minimal, you get a local correlation. And all of the local correlations come from these one minimal spaces. Okay, so I am aware of the time. There's I don't want to, I want to leave a little space for questions or something. And there's 15 minutes left of the hour. So I had one more third of my talk that I'm going to try to just kind of summarize very quickly so that I can say the thing I promised at the beginning of the talk. Okay, so what we've done is shown that you can get these different classes of correlations from these abstract operator systems. Those are just vector spaces with some order structure. But if you hand me a correlation, I have to then produce some operator system that spits out the correlation. It would be nice if there was a single operator system that I could always go to, and that gave me every correlation by just varying the different states. And it turns out there is a way to do that. And not only does such a thing exist, we can build it in a constructive way. We can actually construct the positive cones that give you that space. And I'm just going to kind of thumb through some slides about that. So we call these universal projection systems. So basically, if you have such a thing, you can get all of the correlations by sort of composing a state on some random operator system with a projection that takes you from this universal space into the random operator system. And so we have this universal quantum commuting operator system. And the construction doesn't actually depend at all on these non-signaling relations. You can do this for any set of relations. So let's say I have a set of vectors. So E represents my unit, P1 through Pn are going to represent my projections. And let's assume I have a set of relations R on those vectors. It could be the non-signaling relations. Maybe these are the QABXYs, and I enforce these non-signaling rules on them. Or I could have some other just linear equations that I ask these things to satisfy. We'll say an operator system is universal with respect to these rules if whenever I have another operator system spanned by a unit, let's label that unit F, and some projections, call them Q1 through Qn, which also satisfy the same relation, then I get a map pi from the universal thing to the random thing. Well, sorry, I can write down this map. It sends the unit of the universal space to the unit of the random thing, and it sends the pi of the universal space to the qi of the random thing. If that is positive, or actually completely positive, so I ask that it somehow preserves these positive cones at all the levels. If that always happens, we'll call it a universal operator system with respect to those relations. And so this is ongoing work, I guess. The preprint will appear in the next month or two. With Roy Areza, we can show that given, as long as there exists an example of an operator system spanned by a unit and projections satisfying those relations, then there's always a universal one. And not only does it exist, we can construct it. We have a recipe for building this thing. And now I'm just going to thumb through the recipe here because I don't have time to speak about it. So there's sort of an inductive limit process of building these different positive cones. Okay, so we construct that thing. I want to add that we can also do this with a de-minimality condition. So we can also build a universal operator system with respect to these relations, which is d-minimal, which embeds into this direct sum of d by d matrices. And it has this universal property. If I have another operator system spanned by projections satisfying the relation, which is d-minimal, which also embeds into direct sum of d by d matrices, then I can map from the universal thing into the other thing. And using this, we can say some things about correlations. We can, there's a single operator system that produces all of the quantum commuting correlations, and we have a construction for it. For the quantum correlations, there's a sequence of them that we have to choose from. You get a quantum correlation by applying a state to one of these phi d's, these d minimal universal things. And then you get the local ones from this one minimal universal space. So we have a more compact way of doing this. And more importantly, we have a construction for building it, which we hope someday maybe we can use that construction to actually compute something. And maybe this gives us some other approach to the Kahn embedding problem. Okay, and the last thing I want to say is a vague possible connection of this idea to seek POVMs and mutually unbiased bases. Okay, so there's various ways to define this, but a seek POVM is essentially a set of projections, Q1 through QD squared, rank 1 projections in the D by D matrices, which satisfy some conditions. If I take the Hilbert-Schmidt inner product, the trace of the product of two different projections, I get this fixed constant. And also if I sum the projections together, I get D times the identity matrix. So this is one way you could define a seek POVM. And we believe they exist in all dimensions D, but there's no proof yet. We have numerical evidence up to some level, and probably many of you know a lot more about that than I do. So you could phrase this in terms of this language of universal spaces. Here's a relation, let's call it seek. Well, let seek denote the relation. I have D squared P's and they sum to D times the identity. Well, I can construct a D minimal universal system, operator system, and it has the property that it surjects onto any other D minimal operator system with projections satisfying that relation. So that's always going to be completely positive. In particular, if I have a seek POVM, the map sending the unit of the universal thing to the identity matrix and the PIs to the projections in the seek POVM, that's a completely positive map. And we have a kind of concrete way of constructing this thing. So I don't know if this tells us anything at all about seek POVMs. That's probably very optimistic. But maybe there's something we could learn by analyzing the construction of this thing. Lastly, I'll just say you can say the same thing about MUBs, mutually unbiased bases. So if you have a maximal set of them, let's say you have a bunch of projection valued measures with a certain tracial inner product. The fact that you have these different projection valued measures, you could take that as your relation. You could form a universal D minimal space and you get this completely positive map. Does that say anything about the existence of maximal families of mutually unbiased spaces? I don't know, that's probably optimistic, but it'd be interesting if it did say something about it. All right, thank you for your patience.
All right, thanks so much.